This video examines the tuning of the baghouse inlet temperature controller. Our starting point is the process at its normal operating conditions. The hot air pressure controller and the hot air temperature controller are on auto. As the baghouse inlet temperature controller is currently tuned, the controller gain is 10% to percent and the reset time is 2 minutes. In most loops, a controller gain of 10 would be suspicious. But temperature loops are an exception. Even higher values are commonly encountered. Temperature measurements are generally free of noise, so large controller gains can be tolerated. When the PV input range reflects requirements such as process startup, the PV span is often far wider than required for control. For this loop, the input range is 0 to 200 degrees Celsius. The 200 degrees Celsius span is probably 4 times larger than required for control. If the input range were changed to 50 to 100 degrees Celsius, the 50 degrees Celsius span is 1/4 of the original 200 degrees Celsius span. The controller gain would be 2.5 instead of 10. The baghouse inlet temperature is the result of mixing 2 gas streams. The dynamics should be very fast. This is not consistent with a reset time of 2 minutes, which reflects the slower dynamics of the furnace. Switch the temperature controller to auto. Then change the set point from 70 to 75 degrees Celsius. The baghouse inlet temperature is assigned to the yellow pin. Initially, the temperature increases rapidly, but a peak in the temperature occurs well before attaining the set point. This behavior is often called humping. Place the simulator in hold. The initial rapid rise is typical of mixing processes. On the increase in the set point, the controller opens the hot air damper to baghouse inlet. Initially, the increased hot air flow causes the temperature to increase rapidly, which would be expected for a mixing process. But there is a second consequence. The hot air temperature, the red pin, decreases significantly. Opening the hot air damper causes the hot air temperature to drop about 12 degrees Celsius. The dynamics of the hot air temperature response are consistent with the dynamics of the furnace. Additional hot air flows through the damper, but the air is cooler. Consequently, the initial rapid rise in the baghouse inlet temperature is not sustained, and hence the hump in the response. The current tuning for the baghouse inlet temperature controller reflects the slower dynamics of the furnace. To reflect the dynamics of a mixing process, the tuning for the baghouse inlet temperature controller should be a shorter reset time and possibly a higher gain. Increase the controller gain to 20% to percent. Then switch the simulator to run. Change the set point to 70 degrees Celsius. The response exhibits a more rapid initial response, with the hump closer to the set point. The peak or hump is not associated with an oscillation. Consequently, we could either increase the controller gain or shorten the reset time. Increase the controller gain to 30. Then change the set point to 75 degrees Celsius. The hump is even closer to the set point. Shorten the reset time to 1 minute. Then change the set point to 70 degrees Celsius. Hump's a little sharper, but otherwise not much has changed. Shorten the reset time to 0.5 minutes. Then change the set point to 75 degrees Celsius. The initial peak or hump occurs near to the set point, but with some increase in the degree of oscillations in the response. Shorten the reset time to 0.25 minutes. Then change the set point to 70 degrees Celsius. The initial peak is above the set point, so technically the hump is gone. Place the simulator in hold. The controller tuning is now consistent with the dynamics of a mixing process. However, the impact on the hot air temperature loop is a concern. The hot air temperature is assigned to the red pin. Decreasing the reset time for the baghouse inlet temperature controller from 0.5 to 0.25 significantly increases the oscillations in the hot air temperature. Aggressively tuning the baghouse inlet temperature controller has a consequence. The rapid changes in the hot air damper opening are disturbances to the hot air temperature loop, and thus the oscillations in hot air temperature. But changes in hot air temperature are disturbances to the baghouse inlet temperature loop. The oscillations observed in the baghouse inlet temperature are due to these disturbances. The next video will examine the tuning of the scrubber duct inlet temperature controller.